This is Team Kowalski Analysis, and we present to you our work on variegated machine unlearning. As we know, for training machine learning models, the data is gathered from various sources. There is a possibility that the dataset is poisoned, which means some data items are incorrectly annotated or some noise is added in the data. This may cause issues when this model is used for inference. To address this issue and remove the adverse effect of poisoned data from the dataset, we use machine unlearning, in which we allow the model to forget previously learned information or patterns. We have experimented with certain scenarios that one might face while doing some machine unlearning in practice. Our objective is to evaluate the adverse effect of false poison detection and class imbalance through rigorous experimentation and analysis. In this project, we have extended the work done on corrective machine unlearning. The idea behind corrective machine unlearning is to remove adverse effect of poison data from the model even if a small number of poison samples are known. Various unlearning algorithms like exact unlearning and catastrophic forgetting were being used in the experiment. We are planning to experiment two different scenarios using machine unlearning algorithms. The first, false poison detection. While finding poison data for removal from the training dataset, model developer might delete some clean data unknowingly, or the algorithm might unknowingly flag clean data as poison. We tested the effect of removing false poison data with different fractions of clean images. The fractions of images, the clean images identified as poisons that were used were 20%, 30%, and 40% of all poisons. The second scenario is that of class imbalance. The problem of class imbalance is prominent in the field of machine learning. We consider the impacts of poisoning and unlearning under such scenarios. In particular, we consider corrective machine unlearning, where some of the poison may go undetected. Coming to the implementation, the dataset used in both of these experiments was Sephartin with some minor modifications, as mentioned later. The model used was ResNet9, with a custom implementation. Looking at the class imbalance implementation, we consider the problem, and in datasets, the impact of machine unlearning of problems under such settings is considered. The dataset here is Sephartin. Only dogs and cats are considered. We choose cats and dogs for their similarity and subsequent difficulty to distinguish, relative to say cats in ships or dogs in trucks, etc. Similar to the previous experiment, the model used is ResNet9. We choose a relatively small model as our dataset is small in size. Training is done on a dataset with 5,000 dog images and with fewer cat images covering varying degrees of imbalance, with cat to dog ratios 0.2, 0.4, 0.7 and 1.0, that is 1000 cat images, 2000 cat images, 3.5 thousand cat images and 5000 cat images respectively. Poisoning. We consider a simple poison where we apply a patch of size 3 x 3 to the bottom right or top left corner of the image respectively for cat or dog images. The simple nature of the poison allows for the model to easily learn these shortcuts. We poison 100 images from the trained dataset in total. We vary the fraction of poisoned cat and dog samples between 0.2 and 0.9. That is, either 20 cat samples are poisoned or 90. This allows us to study the performance of unlearning methods relative to the degree of poisoning of the smaller class, here cats. Poisoned images labels are swapped, that is, cats are labeled as dogs and dogs are labeled as cats. Some sample poison images are added here. Images are for reference purposes only. We explore true tried and tested unlearning methods, catastrophic forgetting, and exact unlearning. Overall, we observe that across experiments, exact unlearning outperforms catastrophic forgetting, which agrees with the existing understanding of the two methods. We create a test dataset with 1000 cat and 1000 dog images. The distinction to not have imbalance in the test dataset is important, as that allows accuracy to better capture the model's performance on the small class as well. As the smaller class gets a 50% representation in test, thus poor performance on the smaller class would proportionally impact test performance. We perform evaluation on two sets of test datasets. One, as discussed above, without any poisoning of test images. Another, an adversarially generated test dataset where every image is poisoned. This helps us evaluate performance against the adversarial case, where adversaries may add Trojan attacks or or poisons that act as Trojans. Here we look at the results of our experiments. The effect of false positive detection on accuracy is observed as follows. We see a sharp dip in accuracy after a certain threshold. Effect of unlearning poisons over class imbalance. Observations. In case of removal of false poison samples from the dataset, we observed that up to 20% of removal of the clean dataset, the model accuracy is around 88%. But if the fraction is increased up to 30%, the model accuracy is dropped significantly to 34% and is getting reduced further. We observed that performance over the adversarial test in the second experiment improves upon unlearning poison. Greater improvement when removing higher number of poison samples. Performance is also worse with greater degree of imbalance. While the aforementioned results match expectations, it is interesting to see that when the degree of imbalance is high, say the cat fraction is 0.2, a larger fraction of the smaller classes samples is poisoned, unlearning gives better results. This is contrary to expectation, as it was believed that a higher degree of poisoning of the smaller class should lead to worse performance, because the smaller class has an equal representation in the test dataset and adverse performance over the same would lead to poorer performance overall. The poisoning used is straightforward and easily confuses the model, acting as a Trojan or a shortcut. While model performance is mostly consistent on clean data, when unlearning, we find that for high degree of imbalance, greater poisoning of the smaller class leads to better overall accuracy on the adversarial test dataset. We hypothesize that this is likely due to the model performing poorly on the smaller class regardless in such cases. With greater amounts of poison in the smaller class, the amount of poison in the larger class, that is the dog class, is lesser, and thus the poisoning has a lower impact on the larger class, which the model performs better on. And thus, overall, after unlearning, the model has better performance on the larger class and better performance overall. Also, we find that as the degree of imbalance reduces, say when we have a high ratio of cat fraction 0.7, we see that the impact of the poisoning ratio on performance changes to match our expectations, where a large degree of poisoning of the smaller class leads to worse overall performance, as now this agrees with our above hypothesis as well. After a certain degree of imbalance, the assumption that the model performs poorly on the smaller class, regardless of poisoning fraction, is not expected to hold. And then, thus, we can say that poisoning of the smaller class has higher effect on model performance in such cases. Thank you.